Hello, today we're going to talk about Newton's third law. So we've already learned about the first and the second law. Just for a review, the first law says that if the net force on an object is zero, then the object will not be accelerating. So it will neither speed up, slow down, or change direction. The second law says that if there is a net force, then it will accelerate, and the acceleration is directly proportional to how much force you apply and inversely proportional to the mass. So all the problems that we've worked so far deal with one or the other or both of those two laws. Now we're going to look at what happens when you have more than one object interacting with each other, and that requires us to bring in the third law, which deals with the idea of the interactions between different objects within a system. So anytime two objects exert forces on each other, we call that an interaction. So for example, imagine that you hit a nail with a hammer. When you hit the hammer with the nail obviously exerts a force on the nail. We can tell that. But the nail also exerts a force backwards on the hammer. So this interaction involves two forces, one on the nail and one on the hammer. Same thing happens when you hit a ball with a baseball bat. So when you hit the when you hit the ball with the bat, you're going to exert a force on the ball. That's the whole point of hitting it, right? But the ball also exerts a force back on the bat. When you pull somebody in a tug of war, that person pulls back on you. If you're sitting in a chair right now, you push down on the chair pushes back up on you. Those are both normal forces. These are not isolated incidents. In fact, all forces, every force that comes in pairs. And we call these action-reaction pairs, or Newton's third law pairs. Let's look at the bat and the ball again. The bat hits the ball. It exerts a contact force. In this case, it's a kind of normal force because it's two surfaces pushing against each other on the ball. And the ball exerts that same amount of force, but backwards on the bat. So making that more general, no matter what the objects are, whether you're talking about a hammer and a nail, a bat and a ball, your foot in the ground, or whatever, anytime two objects interact with each other, there will be forces exerted on both of those objects. And those forces we call an action-reaction pair. So if object A exerts a force on B, B exerts a force back on A. We usually designate that using these little subscripts. So FA on B, FB on A. So B on A would represent the force that B exerts on A, while A on B represents the force that A exerts on B. So far, we've primarily considered just single objects. We haven't looked at any problems where we have more than one object that might be affecting each other. And when we had a single object, what we did was we draw a free body diagram similar to the one shown here. We would add up all the forces and we would use that to figure out the acceleration. Or if we knew the acceleration, we could use that to figure out some of the unknown forces. Well, we're going to do similar things, but remember that when we make these free body diagrams, they're mainly just for one object at a time. So we kind of have to be careful when we start to get into problems with more than one object that are. So in this chapter, we're going to extend that simple particle model to include two or more objects that interact with each other. As we see here, what if we had three objects that are all exerting forces on each other? We can show, by drawing a line here between them, we can show that there's a force here between B and C, right? C exerts a force on B, B exerts a force back on C. There's also a force here between A and C. And then there are forces between A and B. Like I said, we usually label these by saying F with the subscript, like A on B would be the force of A on B, or A on C would be the force of A on C, and so on. Now let's make that a little more specific. Let's just go back to the hammer and nail example from the very beginning. The same object, A is the hammer, B is the nail, and C is the earth. The earth is obviously interacting with both the hammer and the nail, right? It's exerting gravitational forces. What you may not realize is that the hammer and the nail are also exerting gravitational forces on the earth. They have to, right? All forces occur in pairs. If the earth pulls down on the hammer, then the hammer pulls up on the earth. Why is it then that if we drop the hammer, we see that it falls very rapidly toward the earth with a big acceleration where the earth doesn't appear to move? Well, remember, Newton's second law tells us that acceleration is directly proportional to the force. So the force is the same on both of these objects. It's also inversely proportional to the mass of the object. So which has a bigger mass, the Earth or the hammer? I think we all know the answer to that, right? Obviously, the Earth. So even though it's the same force, the effect of that force is very different. It affects the hammer a lot more than it does the Earth because of the difference in the masses. When we do problems with interacting objects, it's often helpful for us to define what is actually in our system. So we define the system as any objects whose motion we want to analyze. We can have 1, 2, 3, 4 more objects inside our system, and then everything else we consider to be the environment, or things that may be exerting forces from the outside on the system. We can show this in a diagram. We're not going to spend a lot of time making these diagrams, not like we have for free body diagrams, but it is helpful to visualize how these forces are interacting with each other. So again, if we think about the hammer and the nail and the nail are both exerting forces on the Earth is exerting forces on them. In this case, the Earth down here, C, is considered to be outside our system. It's considered to be in the environment. But there are also forces within the A and B are exerting forces on each other. You're right. So there are interactions within the environment. Forces that are inside the system, we call those internal forces or internal interactions, and things that are coming from outside the system, we call those external forces or external interactions. Let's look at an example of how we might identify what forces are acting on the objects in a situation where you do have interactions between multiple objects. So let's look at an example of a person pushing a crate. Here we have a picture. A person pushes a large crate across a rough surface. We want to identify all the interactions that are going on here, show them on the interaction diagram, and then draw free body diagrams of the person and the crate. The person on the crate are obvious objects here that we want to consider. We can make those to be inside our system. There's a pushing force that's connecting them, right? Which is again a kind of normal force, but we'll call it something different so we don't have so many of the same name. So they're exerting forces on each other, but there are also interactions with the ground, right? The surface, which is represented by S here. Now there are two interactions with the surface. You have normal force and friction force. They would not be in necessarily the same direction, but we have both of those being exerted on both the man and the crate. And then finally we have the Earth. We label that with EE. So the entire Earth exerts gravitational forces on both the person and the man. Now let's think about translating that into free body diagrams for the person and the crate, right? So if we have the person, what forces are acting on the person right now? Well, we have the force of gravity, right, from the Earth. Let's have the normal force that the ground is pushing back up. Now, once again, just like the Earth is pulling down on the person is also pulling up on the Earth. The person is pushing down on the ground is pushing back up on the person. We have also the force that the crate is pushing back on the person, right? So the crate is pushing on the person this way. I'll call this FC on P for a force of crate on person. We also have a friction force. Now we have to be really careful here. It's tempting to draw the friction force in the same direction that the crate is pushing, so backwards, because the person is trying to move forwards. We always think that friction force is opposite the way that the motion is occurring, and it is. But you have to look at what's happening actually on the ground, right at the point where your foot is making contact with the ground. So when you put your foot against the ground, you actually push backwards against the ground. So your foot is trying to slide backwards. So the ground will exert a static friction force forward against your foot. So we have a friction force and static friction because your foot is not sliding across the ground. It's sticking and then pushing backwards. Now what about for the crate? How is this situation different? Well, the crate also has force of gravity acting downward on it. It has a normal force acting up. as the force that the person is pushing on the crate. So this force here and this force here are equal. They're going to show up in both. They're going to be the same force. It also probably has a friction force. Now, presumably, once the person gets it moving, this is going to be kinetic friction force for the crate. One important thing to think about here is we can use these pictures to figure out how the crate is actually able to move. Because a lot of people think that if the crate pushes back on the person with the same force the person pushes on the crate, then how is the person able to actually move? You know, you don't have to push against the crate harder than it pushes against you in order for you to move, because to determine whether something's accelerating, you have to look at all the forces that act on it. If we look here at the person, right, the force that the crate exerts on the person is just one force. The person can push down hard against the floor, creating a big friction force. That friction force can be bigger than the force that the crate pushes back, and as long as it is, he can accelerate the crate forward. Same thing over here with the crate. The crate has maybe less friction than the person is able to generate with the floor. And so even though you still have the exact same force that he pushes back, the person is still able to move the crate forward. So when determining how something's going to move, you have to consider not just that one force, but all of the forces. So we talked about this briefly on the last slide, but let's look at it in a little bit more details. How do we actually walk? This is an interesting concept to me. If you try to walk across a frictionless floor, imagine what would happen, right? When you take a step forward, to actually propel your body forward, you push backwards against the ground. Your foot must stick to the floor as you straighten your leg and then moves your body forward. So what's happening is you have a static friction force between your foot and the ground. Think about if you wear really slippery shoes on the bottom, or if you're just in socks. You can't run as fast in socks as you could in, say, cleats, because you can't generate as much friction force with the ground. So when you push backwards against the ground, the friction force pushes forwards on you. So even though you're walking forwards, you also have a friction force in that same direction, because your foot is trying to slide backwards with every step, and the force is propelling you forward. So we rely on friction every day just to get around. Here are some other examples in which Newton's third law is very important. So when you have a rocket and you want to fire the rocket, how does the thrust force work? Well, thrust force works because the rocket pushes hot gases out one end, and then those gases exert equal forces back upward on the rocket, creating equal forces and propelling the rocket forward. Cars work almost the same way as you walking, at least the purpose of how the tire sticks to the road. So at each point on the wheel, the tire sticks to the road and it pushes backwards as it rolls over that point. So what makes tires actually move is static friction. You may think that static means it's not moving, but that the tire is not sliding across the road, so you don't have kinetic friction. So now that we've had some examples of Newton's third law, let's look at a formal definition of it. Newton's third law formally says that every force in the universe occurs as one member of an action-reaction pair. The two forces that are involved in an action-reaction pair always act on two different objects, and they're always equal in magnitude and opposite in direction. A lot of times you hear Newton's third law said as in this way: for every action, there's an equal and opposite reaction. You've probably heard that in many classes before. And that's true, but I think that definition doesn't really capture exactly what Newton's law is really all about. So I like to think of it, if you want a short, kind of catchy phrase, is that all forces occur in pairs. That's the way I think of Newton's third law, because that's really what it's telling you, is that every time you have one force, you have a paired force that's acting back on the other object, and those forces are always the exact same magnitude, and they're always opposite in direction. So let's think through a couple of examples here of using Newton's third law. So once again, let's think about gravity, because that's a tricky one. When you release a ball, it falls down. As I said earlier, it falls down because gravity pulls down on the ball, but the ball also pulls upward on the earth. And Newton's third law tells us that those two forces actually have to be equal. The ball pulls up on the earth just as hard as the earth pulls down on the ball. So how is it then that the ball accelerates more? Well, it has to do with the difference in their masses, right? The force of the Earth on the ball is equal to its mass times the g, gravitational coefficient. We can use Newton's second law again with the Earth. The acceleration of Earth is going to equal whatever force is exerted by the ball on the Earth, which has to be the same as this force up here, divided by the mass of the Earth. Well, that means that the acceleration of the ball is equal to the mass of the ball divided by the mass of the Earth times g. Well, the ball generously might have a mass of 1 kilogram. In fact, that's a heavy ball. That's, 2.5 pound ball. And the Earth is significantly bigger than that. So even if the ball has a mass of 1 kilogram, the Earth will only have an acceleration of 2 times 10 to the minus 24th meters per second squared. Do you think that's enough to detect or feel or anything? Absolutely not. So does it mean that there is no force there? No, it just means the acceleration is so small that it practically does nothing. Let's think about another question related to this. What happens when a mosquito runs head-on to a truck? Even though the mosquito is significantly smaller than the truck, the forces that are exerted between those two have to be the same. So the mosquito exerts the same force on the truck as the truck exerts on the mosquito. Why then does the mosquito get squashed and the truck just drives on and doesn't even notice it? Well, that's again because of the difference in their masses. So just like the ball in the Earth, the truck is a lot bigger than the mosquito. So that same force has a much bigger effect on the mosquito than it does on the truck. So think about that same situation. Even though the forces are the same, does that mean that the acceleration is the same? Definitely not. Remember that acceleration is proportional to the total force divided by the mass. So if they have the same force but have different masses, the accelerations will be very different. So the magnitude of the mosquito's acceleration is larger, much larger than that of the truck, and that is why the mosquito ends up smashed. All right, let's finish today with analyzing a somewhat complicated situation where you have a hand pushing two boxes A and B to the right across a frictionless table. The mass of B is bigger than the mass of A. Let's try to draw free body diagrams of A, B, and the hand and figure out which of these forces need to be equal and which are action-reaction pairs, and then we're going to try to rank in order from largest to smallest all of those forces. And these pieces, just to keep things simple, we're just going to show the horizontal forces. Of course, A and B also have gravity and normal force acting on them as well. Let's look at the hand first. Okay, so the hand pushes on box A, and box A pushes backwards on the hand, giving it a net force to the right, so it would accelerate to the right. The hand, we're going to show those forces here. Start with box A. All right, that's the easiest one. So the hand pushes on A this way, and B pushes back on A that way. The force that the hand exerts on A clearly must be bigger than the force that B exerts backwards on A in order for it to accelerate forward. Now, both of these forces are paired to other forces on other objects. So if B exerts a force on A, right, we can go follow this way. A exerts that same force on B. If the hand exerts a force on A exerts a force back on the hand. In this case, the hand also has another object exerting a force on, and that's your arm. So that's what they have to exert a bigger force. Notice that in all three of these cases, the net force on each object is still to the right. So they're all accelerating to the right. Now that we have the free body diagram, let's see if we can try to figure out which forces must be bigger. Well, in this case, to have an acceleration to the right, the force of the arm on the hand must be bigger than the force that A pushes back on the hand. So the force of arm on the hand is going to be the biggest, right? So it's going to be bigger here than the force that A exerts back on the hand. Well, the force that A exerts on the hand then has to be equal to the force that the hand exerts back on A. That's Newton's third law. So those two things are paired together. That in turn must be bigger than the force that B exerts on A in order for the middle box, A, in order for it to accelerate. And then again, those two forces are paired because of Newton's third law. So the force that B exerts on A has to be equal to the force that A exerts on B.